Hello, so welcome back. In this module, let us understand how data is represented in an ASIC design system. So the first part is binary number system. We are familiar with that. So all the digital logic in an IC design, they operate, they can operate using the two voltage levels in a binary number system, that is logic low and logic high. In other words, we call it 0 and 1. Now, every form of the data will be represented by the combination of the binary digits. For example, you have a decimal number 13 that will be represented in binary as 1101. If it is decimal number 15, the binary form of it will be 1111. Now have a look at how the numbers are represented. So there are following types. First one is unsigned binary. Again, it's binary, that means 0 and 1. So unsigned means it represents only positive numbers. For example, there is a 4-bit number, decimal 5 is represented as 0101, and decimal 15 is represented as 1111. So it is only showing up the positive numbers. However, there is a second type here called as signed binary, which is nothing but 2's complement of a number. So in this form of a number representation, you have both positive and negative numbers. So MSB tells us whether it's a positive number or the negative number. Is basically a sign bit. For example, there is the 4-bit number, which is a positive 6. 0, which is an MSB here, tells us it's a positive number, and the 3 following digits, 110 in decimal, it is 6. If you want to represent the same -6, so you have to obtain a 2's complement of 6. So first, you basically invert this number, take a 1's complement of it, and then add 1 to it. That gives you this number. Here, you can see the MSB1 indicates it's negative signed binary number, and you have 010 that tells it's a number 6 in decimal. You have fixed point representation. So the binary point here is at the fixed position. This kind of number representation is good for doing a fast arithmetic. For example, you are designing an audio DSP, digital signal processing IC. An example here is 0001.1000. That tells us it is 1.5 in Q4.4 format. There you have floating point representation. In other words, it is called as IEEE 754. It is used in complex processes like GPU or scientific applications, breaks numbers into sign, exponent, mantissa. Example is as shown in this figure that tells us it is number 6.5 in IEEE 745 with a single precision. Third form is called as ASCII and character data. For example, letter A in ASCII form is given by this kind of numbers, that is 0, 1, 0, 0, 0, 0, 1. You have Boolean logic then, which is basically a true or false. True is 1, false is 0. This kind of logic representation is used in control logic, state machine, and combinational logic when you design those kind of logics. Then you have vectors and buses. So multiple bits can be grouped for parallel processing. For example, 8-bit, 16-bit, 32-bit, and you say that it's a data bus. And example would be, let's say you are having an arithmetic logic unit, which is a 8-bit ALU that will process this 8-bit of number in one operational cycle. If it is 16-bit ALU, then there'll be a 16-bit data, 16 bits grouped together to be processed in parallel in one operation cycle. So functional blocks like registers, multiplexers, memory, arithmetic logic units, they operate on these representations, and designers who uses Verilog or VHDL, they use this language to describe how these values are processed. For example, you have a RTL code here, which is a Verilog, and you are writing this code for describing an adder circuit. So you start with the module. Name of the module is adder. It has got input uh, data 0 to 3, that is a 4-bit data. And then you have A and B are its 4-bit binary unsigned numbers, what you see here. And the output is again a 5-bit 0 to 4, and that is basically a sum. So you write this syntax here: assign sum equals to A plus B, and then end the module. So sum here is your 5-bit results. That is 4-bit sum and 1 bit to take into account an overflow, if any. So this is how you represent your data in various forms. We've seen that signed numbers, which is the 2's complement of the binary number, unsigned numbers, ASCII numbers, Boolean logic, vectors and buses, etc. So hope you found this module useful. If you did so, share it with others for wider reach, and stay tuned for more engaging content like this. Till then,